So my name is Simon Hughes. Please let me know if you can't hear me. I work at dice.com with a number of my colleagues. And I'm here today to talk to you about evolving the optimal relevancy scoring model at dice.com. Kind of rolls off the tongue. By the way, don't join the danger virus Wi-Fi network. I almost did that earlier. It got a little scary. But that is actually on the Wi-Fi list there. OK, so who am I? I am the chief data scientist at dice.com. I work on the data science team under Yuri Burkov. If you haven't heard of us, we are the leading US job board for IT professionals. We have a booth here, so come check us out. Here's my Twitter handle, HughesMeister. We have a number of key projects that our team has worked on. They're now on the site or on the mobile app. Last year, we released skills pages. So if you go to dice.com/skills, you'll find a wealth of information about technology skills, including Solr, Lucene, Java, and so on, including related skills and trends over time. We also have a new mobile app that launched this May. So that not only has job search, but it'll actually tell you what it thinks your salary should be based on your location, your title, your skill set. And it will also recommend some skills that are relevant to you in your role that you don't know that you might want to learn next in order to get a better salary. Kind of optimize what skill most optimizes my salary. So check that out. It's free on the app stores, both iPhone and Android. I'm also a part-time PhD candidate, which is a bit of an oxymoron. I'm studying machine learning and natural language processing at DePaul. OK, so last year, we really felt like we wanted to share the code that went with the talk so you guys could follow along at home. There's no surprises, no magic. All the code was open sourced. So once again this year, we've done the same. So you'll find a number of GitHub repos under github.com/dicetechjobs. There's a repo of Solr plugins under the Solr plugins directory, and then there's a new directory called Relevancy Tuning. That is a Python notebook tutorial guide for following along with the stuff I'm going to talk about today. Last time I gave code with a talk, people appreciated it, but they found it hard to follow. So I tried to make sure that the code is self-contained. It includes a pre-indexed Solr collection, some dummy data that you can index on it, the schema, the XML, and then the code to run optimization on it. So it should have everything you guys need to do to at least try this stuff out on some fake data. OK. All right, so what am I here to talk to you about today? My main focus on this talk is going to be approaches to relevancy tuning. As part of that, I'm going to talk about ways in which you can automate the relevancy tuning process, so it's not just a manual process of tweaking the configs. There are some more sort of scientific and disciplined ways that you can go about doing that. And lastly, if I have time, I want to talk very briefly about the dangers of feedback systems when you have self-learning, self-optimizing search and recommender systems. So why did I want to talk to you guys today? Well, a number of reasons. Last year, I talked about conceptual search and the ways in which you can improve recall in your search engine. So this year, I wanted to focus more on precision. What are the ways that we can improve the precision of our results? I also like to talk about something that I haven't seen people talk about before. So that's also part of the motivation for this talk. OK, so the basics. Relevancy tuning. So how do we find the optimal search engine configuration? Right? Most companies, including ourselves, approach this in a somewhat ad hoc manner. They take a set of queries, they take the Solr configuration or whatever search engine you're using, and they follow some best practices and run some queries, do some tweaks to the configuration, see if the results get any better, and then iterate on that. There's nothing inherently wrong with that, and it's certainly a good way to learn how your Solr or your search engine works. However, that always bugged me. I always wanted a more scientific a way to approach that, particularly a way to automate it, if possible, or parts of that process. Also, the search engine parameters and really the configuration of your search engine should really reflect how your users search. They should not reflect how your business analysts think people search. They shouldn't reflect how your QA department or your sales team think a user search. Unlike a lot of the complaints we get are from the sales guys, and so we're trying to fix problems from sales, and some of those are valid problems, but really what is important is, are the users getting the results that they want? Right? Relevancy is a hard to define concept, but the easiest definition is it's whatever your users tell you it should be, right? I mean, in my opinion anyway. Like, relevancy is what is getting the best results for your users. So I'm going to talk, part of my talk today will cover how we can use search log capture to get that data and use it to tune our algorithms. So what Solr options generally influence relevancy? What are some of the important ones? Well, there's many Solr and Lucene options that impact the accuracy of your results. Which query parser you use, which field boosts, and what settings. Do you have phrase boosts, and do you use PF and PF2 parameters? What setting do you use for the MM parameter, right? Do you have an AND search, an OR search, or somewhere in between? Do you require every term to be matched, or some of the terms? Which similarity class do you use? Do you use BM25 in the new, which is the new default, or do you use tf.idf or something else? Do you make use of boost queries? And the EDS max type parameter, do you use that at all? I'm not going to go into those and what my recommendations are. They're on the slides, but there's not enough time to go over that. Okay, so what I'm going to argue is that to come up with the best relevancy, you really need a golden test collection or a test data set of some kind. What do I mean by this? Well, I mean by a set of queries, ones that you believe are important to your users, and then a set of relevancy judgments for the results of those queries. Now, there's several ways you can go about collecting that. One would be you have a set of domain experts, so it's business analysts or QA people or just some sample users, and then you have a user interface designed to capture those judgments. There are a number of good commercial examples for this, Cupid being one of them, developed by open source connections. Fusion also has a relevancy workbench, I'm told. I haven't used it, but it looks pretty cool.
It's back in 3. It's gone for a while.
Okay. Thank you. So check that out if you have Fusion. We built a simple tool for our own purposes. It looks like this, just to illustrate how this kind of works. So if I do a search for, say, Java developer in Chicago, Illinois, I hit go. I get a set of results, right? And then I simply go through the result set and say which ones are relevant. Now, this does not represent our job search. It is intentionally slightly broken, so just so you know. All right, so Java developers are relevant, those are relevant, and so on. So you provide some kind of rating or accuracy and relevancy as to which of the results you're getting back are accurate. Pretty straightforward. Here's the screenshot. Okay, so that's one approach. That's a good approach to take. Another approach is to use your search logs. So I talked earlier about it's really important to capture what your users think are relevant. Well, you can do that. You can log. Thank you. You can log how users search on your site and capture that data and use that to create this test collection. So how do you do that? Well, you simply need to capture for each query that is executed, when it executed, the query, the filters that we used, and which results people looked at, and which of them they clicked. We can then make the assumption that results that were clicked on, that were viewed, are probably more relevant than results that weren't viewed. You can also take this further, and you can say, if a person spends 2 minutes looking at a result page, it's more likely that's more relevant than if they spent 5 seconds and then went back to the search page. So you can take this data, you can capture it, and you can aggregate it, and you can get a good idea of how users are searching on your site, which gives you a whole suite of good metrics. But you can also use that to create a test collection that you can then use to tune your search engine. So now we have a text collection, whether that's acquired by manually annotating some results or from our search logs. And once we have that, we can use that to tune our search engine configuration. We can try different settings, different field boosts, different settings, different phrase boosts, and so on. And then we can measure the effect of those changes on our data set using an information retrieval metric. There's many different metrics out there. Some of the more common are mean average precision, precision at K, and NDCG, normalized discounted cumulative gain. Don't ask me to say that after a few drinks. It's a little bit of a tongue twister, but I'm not going to go into the details of those. But I will mention that the precision-based metrics are really geared around binary relevance judgments. If you have a rating scale or aggregated counts of result clicks, NDCG will give you the ability to leverage that more nuanced data. And that is what a lot of the big search giants use, from what I've seen. So now you have this test collection and a way to measure relevancy on it. So you measure relevancy by simply changing your parameters, running the same queries on that data set that you have, and just seeing other results that people annotated highly coming back, or other results that people clicked on more, getting to the top of the results set. Now you can use that to do a number of things. You can use that for regression testing. One of the problems with query tuning is you get some query that someone's complained about, and then you tweak your configuration to make sure that it works. Well, a big problem with that is that could break 10 other queries, and they could be very rare queries, so you may not see that those get broken. So you have a test collection. You can then use a regression test suite, run against run all of those queries with the new configuration that you just tweaked to make sure none of them were negatively impacted. Even better, if you have that from your user logs, you have thousands of queries, including a very long tail of queries that you wouldn't get from manually annotating results, and you'll see which of those are also impacted. So that gives you more confidence that that changes did not break something serious. All right, so now we have this. We can also use it to do relevancy tuning, right? But we could do this manually, and there's nothing wrong with that. But is there another way we can do it? Is there a better way? Well, I'm a machine learning guy, so my first thought was, can we use supervised machine learning? That is, we have some labeled data. Let's run an algorithm, have it learn from that, make some predictions. That's fine for machine learning ranking because you're using a machine learning model to re-rank the data. But here, we want to just change our search engine configuration and see what the best settings are. So without going into the details, you can't really do that with a supervised machine learning algorithm. Reason being is that you have the Solr algorithms that implement the relevancy, and you can't compute a gradient over those. You can't interrogate them in some way to know how your changes impact relevancy. So the only way that I know of is to do some kind of search approach. And when I say search, I mean searching for different parameter settings, not Solr search. Kind of confusing. So a naive way to do that is using grid search, or a kind of brute force search approach, where you just try every possible setting you can think of. And that may work. But that's very slow, very efficient. If you have 10 or 20, 30 different parameters, you probably never find something that's really a good subset of those settings that will give you the good relevancy that you want. So an alternative to that is to use a set of optimization algorithms called Blackbox optimization algorithms. And they're called Blackbox because they know nothing about the thing they are optimizing. All they know is they have a set of inputs, and they have an output, and they're going to try and find out which set of those inputs gives you the maximum or minimal value for the output. And these algorithms perform a much smarter search of the parameter space than, say, grid search in general. All of the algorithms that come into this class are called reinforcement learning algorithms, or are used in the field of reinforcement learning, which is also a field of machine learning. And reinforcement learning is an algorithm, or a type of algorithm that learns from interacting with something. We use it to train robots to do tasks and train cars to drive and so on. And they're even used to rank news articles on Yahoo, or they used to be used for that by Relevancy. So these algorithms perform a slightly more intelligent search of the parameter space than, say, grid force search. And so we can use these algorithms to auto-tune or attempt to auto-tune our Solr configuration. So to give you an example of that, I created this little UI here. So I wanted to first illustrate. This isn't really how I would use it, although it might be a cool enhancement. This is more for illustrative purposes. So this is a modification of the UI I showed you earlier. So if I do a search for data science in Chicago, I get a lot of results back. Those results are based on this set of QF, PF, and so on values here. So if I go for this result set and I make some relevancy judgments. So first of all, so we launched our job search on Solr about the start of last year. One of the first problems I encountered with that, in the relevancy domain anyway, was companies' searches. So about 5% of our users search for companies on our site, right? So we're a job site. We have jobs from Amazon, from Google, and from lots of other companies. And a lot of those companies have technology terms in their title, like data. There's a company called NTT Data that is on our site. And data services, lots of companies with technology in their name, and so on. So the way Solr was set up before I came along, someone would do a regular search for a job title, and they would get a lot of matches on the company, because we boost company quite highly. So this was a problem. So there's various ways we got around to solving that. So I'm kind of illustrating that problem here. So I have set the configuration up such that we get a lot of bad matches on the term data for a company. So this is it's not totally contrived in that this is an actual problem that we had. So if I go through the results and say, which of these are data science positions? Scrolling down, scrolling down, scrolling down. OK, here I got one, way down there. And here, I missed the data again. You see we get a lot of matches on the company towards the top there. Right, Cogent Data Solutions, and so on. So I'll go down again. So if I pick the ones that I think are data science roles, which I think there was 5. Keep going, maybe that's it. Right at the bottom there. I think I got all of them. OK, and then I hit my little optimize button here. It goes away, runs the optimization algorithm. Comes back with a result set, with a set of configuration parameters. Gives me an NDCG score. So as this was a single query, it found it quite easy to optimize. So I got a perfect score in the NDCG, which is of 1. And you'll see all my results on the right are now ranked according to relevancy. What's more, I got some additional results here that I didn't get originally from the original query. So generally how I'd use this is to run it as a batch process offline on a bunch of queries. But for illustrative purposes, or even as a way to do sort of augmented intelligence when you're manually tuning, I think this kind of example kind of makes sense. OK, so how does that work? Well, so basically, as I mentioned, the black box is really basically a set of Solr parameters on the input side, and then your IR metric judgment on the outside. And it's going to run those settings on your test set, compute the IR score, and it's going to tweak those parameters until it has a better mean average precision or NDCG or whatever. So here's some example code. This looks very similar to the code I posted on GitHub earlier. So at the top here, you'll see my IR metric. I'm using mean average precision at K. Second function here is get Solr parameters. So what the algorithm does is it generates lists of numbers. So we have to take those numbers and we have to map them into a Solr configuration. So here I'm just very simply taking those 12 numbers and then mapping them to the QF, the PF2, and the PF parameters as boosts over our 4 fields. Then we have the objective function. So this is the black box that the algorithm is trying to optimize. That black box takes the list of numbers, it maps it to the Solr parameters, and then it runs a set of searches with those parameters where we have relevancy judgments for those results, gets them, computes mean average precision, multiplies that by -1, because the algorithm we're using is trying to minimize that score, so we just negate it and return it. At the bottom here is an example of how the algorithm would call, the black box would call the objective function, giving it a list of numbers, and then you get the NDCG score or the map score or whatever at the bottom. So that's all the code I'm going to show you, I promise. Okay, so how do we make this work? Well, a number of good, mature libraries for doing black box optimization. One of them is DEEP, distributed evolutionary algorithms in Python. So that was a sort of inspiration for the name of the talk. However, I'm actually using scikit optimize that came out very recently from CERN. It's a sort of general optimization library built by a team at CERN, headed by Tim Head. And that is the library I'll be using in that tutorial that I posted. It's actually very easy to use it in terms of actually just coding against it. It's actually a lot harder to get it to do what you want it to do, which is to optimize your parameters. But they are very easy to code against. So one of the experiments we did with this was to try to auto-tune our MLT handler implementation. We have a custom version of the Solr MLT handler that's in the plugins repository. And then we do matches on documents based on skills and title and a few other factors. And then we use that to tweak the boost on that MLT handler, and we got about a 5% improvement in map score. We are currently repeating this process using our search log capture and some manually annotated relevancy judgments and seeing what different results we get there. And then we'll be A/B testing them, hopefully, by the end of the year on the site to make sure that they are better than the actual production settings already. So A/B testing is another excellent approach here. If you have a new configuration that you want to test and you actually want to test it against your users, you simply run an A/B test. Right? Solr in particular is very easy to pass in parameters to your search query on the URL. So it's very easy to have a test suite, which is what we've built, to take a set of settings and divert a subset of users or subset of queries to that B group, that test group, with the new settings and see if you get the improvement in the metrics and the KPIs that your company cares about. And that will be the absolute best way you will know that those settings are better, is to run an A/B test and run a statistical test on those results. And so that is the framework we're moving towards. But you cannot test thousands of parameter settings that way unless you're Facebook. So, or run experiments that way. You're going to want to use something like this first to give you a few things to try that you think are going to work, and then run A/B tests on them. And at least that would be my recommendation. So some sort of caveats, because like I said, these algorithms are easy to use, but hard to get them to optimize what you want them to. So if you give them too many parameters to tune, it becomes very hard for them to make sense of the data. So I will start with a very small subset, ones that you think are the most important, and then optimize those and keep everything else the same. If you're using the search logs, you want to use a large number of searches or aggregate result clicks across a lot of users using the same search to get a more robust and aggregate data set. Because some users will just search your site in kind of weird ways, so you want that don't necessarily reflect how most people search. So if you do the aggregation, it will help to drown that out. For most search collections of a reasonable size, this optimization process will take a long time, because for each call of that black box function, you're running a set of queries. So this is something that will potentially save you manual time, but it will take a long time of computing, a lot of computing power and time to run it to get to where you want. So be aware of that. It's not going to run as fast as that little demo, because I was just tuning a single query, and you guys can't sit waiting for an hour for that to happen. My recommended approach, based on my experience with this, is if you have both search logs and manual judgments from users, that you first use the manually acquired relevancy judgments to set an initial baseline of configuration settings for your server. Once you have that, deploy those to production, run an A/B test if it's not a new server, make sure they're better, and then use the search logs to capture data about how your users actually search, and then further refine your configuration from there going forward. So one important point that I really wanted to stress, and then if there's one thing you remember from my talk, other than me whittering on, is this slide. So there was a lot of talk last year also about using test collections, and I'm assuming some people are doing this, but no matter how you take a data set and tune your configuration parameters to it, whether you do it manually or automatically or a combination of both, it is really important that you have a second test set of relevancy judgments that you use right at the end to validate those initial settings. There's a problem in machine learning called overfitting, but overfitting is not unique to machine learning algorithms. Humans can overfit data just as well as any machine learning algorithm. And the problem of overfitting is you have a data set, you've tuned something to that data set, or you've maximized something. If you do that to some extent, the algorithm, the model that comes out of it, in this case your search configuration, will be so tuned to that data set that once you give it new queries or new documents that it hasn't seen before, it will do terrible on those and do great on your original data set. So even if you're just manually tuning your Solr configuration or whatever on a data set, you need to make sure that before you deploy it, the first thing you do is you have some separate second data set and test it against. Ideally, you do k-fold cross-validation and so on, if you know what that is. But you really need to do this, otherwise you'll trick yourself into thinking you've made things better, and most likely you'll make things worse. So some other things to try. You can auto-tune other Solr parameters, like phrase slop, settings, similarity class. It's not just for tuning the field boost. You can theoretically, at least, use it for any different setting that you want to try to tune. You can even involve your own ranking function. I actually wanted to talk a bit more about that today, but I didn't think I'd get it in the time we have available. One way you can do that is you can use the sweet spot similarity class that's provided by Lucene. That allows you to take the default similarity class and control some of the coefficients and some of the values in it. So you could use this approach to try to test different settings there, try to come up with a better scoring function. Or you can take that one step further, and academic researchers have done this. You can use a tool called genetic programming to actually evolve your own ranking function. Right? So genetic programming is a form of evolutionary algorithm that can spit out code or math. So you can have it try to learn, at least, to spit out a different ranking formula. And using the same techniques that I showed here, but a different algorithm, and try to get it to evolve your ranking function for you, rather than use the best practices. You're probably going to have a hard time beating BM25, but you can try different variants of that, or include that as part of your evolved ranking function, and try some clever things there. So I have some links to some papers about that. That's certainly an area of research that was quite active a few years ago. Another point I wanted to make, I strongly believe in the value of machine learning for ranking problems. I don't want you to think I don't. But if you're using machine learning ranking to re-rank your top 10, 100, 1,000 results, but you don't have a pretty optimal search configuration in the first place, then it's kind of a premature optimization. You want to kind of do something like this, some kind of disciplined scientific way of tuning your Solr configuration, whether that's manually tuning or whatever. You want to make sure that that is as good as you can make it before you invest the time and money and effort to both build a machine learning ranking model, capture the data for that, and deploy that and scale it to production. Because that is a very hard problem to solve, and so you want to start with the simple one. And you want to make sure, like I said, that those top 1,000 results that it's returning, before it re-ranks them, are actually the best 1,000, because if they're not the best, it can't re-rank. It's not going to give you good results if it's re-ranking crap. So, relevancy tuning and machine learning ranking, both primarily optimized for precision. I can't stress that enough. So you want the best search engine, you have to also consider recall. These techniques will not give you recall improvements unless you are using additional fields that are providing synonyms or something else as part of your features. So for more ways to improve recall, there's a number of good talks at this conference. There was my own last year. I don't know if that was good, but it was a talk. There's the one from Trey Granger last year and also in 2013, where he talks about semantic search. I believe there's a semantic search pipeline in Fusion. Ted's gone. Okay.
I'm just standing up here so I can see your slides.
Okay. So they have something along those lines. I don't know much about it, but. And then Doug Turnbull and John Berryman wrote the book Relevant Search. It talks about that topic in chapter 11. Okay, very quickly, I want to talk about the dangers of closed-loop learning systems, particularly if you have a machine learning ranking system or a recommender engine that learns from user behavior. So how these systems typically work is that your users are interacting with the system, so running searches or they're clicking on products and stuff. That gives you a data set of relevancy judgments in this case. And then you use that to train some kind of model, right? So, okay, good, we're done, right? Well, what happens if the model's predictions influence how your users interact with your site? That changes how your data is collected. Right, so you have users interacting with the system, right? So to give an example, right, they create data and it builds a model on that data. So a model may say searches for Java, should match Hadoop and various other keywords very strongly. So then that changes the model, which changes how your search works, which then changes how users are searching because they're getting different results back. And then now they see more results for Java searches that have Hadoop and J2EE and so on in the results. So then you get this positive feedback loop if you're not careful, where it keeps emphasizing the same signals because the kind of behaviors it's trying to improve upon are changing how users are searching on the site. That's changing how the data is captured. That's changing the model. And then that's emphasizing those signals even more.
Quick recommendations classic for that because people tend to click on the top things.
Mm-hmm.
And when they become a self-fulfilling prophecy,
Right.
everything else can get ranked.
Right, and most recommenders use a lot of information just how popular something is, and it suddenly becomes more popular if you tune your machine learning ranking system so that it's now going on the top of the page, and it becomes even more popular and so on. So that, as Ted said, that's a great example of that. So to prevent this, there's a number of strategies, and there's a great Google paper on this too. I can give it to you if you want. You can isolate a subset of the data from being influenced by your model, and then use this data to train the system. So you may want to take 5 or 10% of your searches or your users, never give them their machine learning ranking results. Just give them the regular results, and then just take their interactions with the system and just use those to train the model that is used to improve everyone else's results. And you can rotate those users, so they're not always getting the bad results, but you need to be very careful about that. You could generate a subset of recommendations at random using an unsupervised model. It's a little more dangerous, but it may work well in some cases. Another approach, and this is what the Google guy I spoke to about this recommended, was to use a reinforcement learning model to do the machine learning ranking or the recommendations. And as it kind of learns from interacting with the users, it kind of includes almost a negative feedback component so that it will try to make sure that it actually won't have those positive feedback effects. Okay, so that is the end of my talk. Thank you all for listening. And do you have any questions? Gentleman there? Oh, sorry. Thank you. I always forget about the applause part. Sorry.
It was a great talk. Thank you.
Thank you.
One quick question. You use reinforcement learning, but when you train your model, is there still a batch training that's done offline? Or are you actually training online?
So the question was, are we training the reinforcement learning models using a batch process? So in this case, yes. So we're not doing reinforcement learning. We're just using algorithms that are used in reinforcement learning. But there's nothing to stop you actually doing that if you want to do that. Does that make sense?
Yeah.
Yeah. So you don't have to use reinforcement algorithms just for doing true reinforcement learning. And they're not just reinforcement learning algorithms, they're just general optimization algorithms too. Gentleman there?
How do you deal with the combinatorial exclusion in the number of configuration parameters that you are trying to optimize end-to-end?
So the question was, how do we
Combinatorial exclusion?
How do we prevent a combinatorial? Well, that's why I suggest that you don't try to tune a lot of them at once, because you're right, there is an exponential growth in the search space, the parameter search space, if you add in a bunch of parameters. So I would start off with tuning a small number. So you still have to use your brain. It's not completely automatic, right? And say, I think these are most important. I'm going to start with this subset and do it that way. But yes, I mean, there's going to be some problems this way you're not going to work well with because it's just too hard a problem.
Yeah, thank God there's still jobs left for us.
Yeah.
So you guys can get some.
Right. Yeah, I'll be out of a job otherwise. Someone from over there, the guy in the blue T-shirt.
Tuning the search configuration,
Yep.
tuning the search configuration versus using machine learning for ranking.
Mhm.
What order would you use?
I mean, I'm not saying either or. I'm saying do both if possible.
Yeah, in
So,
what order?
and I would start with making sure, like I said, that you have the best search configuration, because most of those MLR models re-rank the top results. So if you're not getting the top results already, and that is determined by your search configuration, then your ranking model is not going to do well. If you change the other one later, then your old training data is have to throw away and retrain it anyway, and recapture that data anyway. So I would start, if possible, with some kind of optimization process, whether you use the Blackbox algorithms or just manual tuning, some kind of manual tuning on a data set. I would start with that. Gentleman in the blue.
Based on what you said, are you using the Blackbox to optimize record more than precision?
So the question was, am I using the Blackbox to optimize recall over precision? Not directly, but that's kind of how it works. So our test set, right, if you think about how we're capturing those judgments, we have thousands or millions, in some cases, of documents. Resumes, it's millions, jobs, it's hundreds of thousands. You're only going to get relevancy judgments from an annotator or from users from the top 30 or 100 results, maybe. So it's really trying to optimize and re-rank those results. There's no way to bring in additional ones because you don't have relevancy judgments for them, even if they're relevant, right? And that's also the challenge with using these algorithms. If they change their parameters too much, then you get a new set of results that may be relevant, but they're so different. You don't have judgments on those also. So I mean, I would also stress is you want to do a very iterative process here. So you want to tune them, deploy it, changes user behavior again, and then gather a new set of judgments, and then retune it again. And don't just do it once. What's the question, Ted?
Yeah, real quick. So since recall involves negative, false negatives, you have to know that the documents that didn't get back should have come back. So how does the engine actually look at the ones that didn't happen and say those were actually relevant, should have come back? Is that how you look at recall failures?
So Ted's asking how we look at recall failures with this. Well, I'm saying that if you capture relevancy judgments that way, you really, if you do a very simple approach, then you're not really capturing recall measurements. One thing I've seen in say, Cupid, for example, which I think is quite clever, is that, so Cupid is an annotation, one of those annotation tools. They allow you to enter a search, and you get the results, and it allows you to enter an alternate search, and then rate those results as if they were returned by your other search. So if you do something like that, then yes, you can have it improve recall. But if you just use the plain approach that most people use, then I don't think it's going to improve recall.
Exactly. Yeah, we also mentioned synonyms, which is a good way, and I guess you wouldn't be able to tune those because those are domain expert.
Right, but you can tune a field that has them.
Okay.
To be one, right. Gentleman in the back.
So you mentioned that,
Sorry.
You mentioned that A/B testing pushed the algorithm to production A/B testing. So what are the techniques that you can, or the limitation that you can determine A is actually better than B?
So I mean, the question was, how do you do an A/B test to determine that your results, your A group or your B group is better? So I mean, it's a very well-studied field. So really, it's a statistical test, right? So you define ahead of time what kind of results you expect and how long you would have to run, how many data points you would have to capture to get a statistically significant result, whatever you define that threshold to be. And then you run the test, make sure you're true to those settings and parameters, and see if it meets that statistical threshold. And if it doesn't, even if it shows an improvement, that could just be due to random noise, and so then you have to throw away and try another test. Does that answer your question? Yeah, I mean, there's a lot of literature on A/B testing that can explain it much better than I can. The gentleman sitting down.
Yep. So you mentioned that machine learning approach to re-ranking, that you need a good first pass search, right, in order for anything to be relevant, in order to train the model. Do you find that you have that same problem though, optimizing the searches, right? Don't you have that same problem, and how do you overcome that? Because how can you judge relevancy in order to optimize the first pass search if the first pass search sucks?
Right.
So you have the same problem with machine learning algorithms. Right?
To some extent. So the question was, do we have the same problem with the optimization approach as you have with the machine learning ranking approach? And I would say, yes, you do. There's not many easy answers to that, as I said. I think you have to do a very iterative process initially. And I would start with the manual judgments, because you can iterate over that a few times. I'm sorry, I'm getting the stop signal. I can talk a bit more outside, though, if you want. Thank you.